We are rolling. Okay, so today, uh, so some actual. Now we get into actual pulse sequences that you actually might run on the scanner, and so I'll start off with the original SpinEcho. You probably wouldn't run that one unless you were a physicist, and then go through two stages. So first there is like fast SpinEcho. There's a way of sort of speeding it up quite a bit, and then on Friday, I'll talk about a really fast SpinEcho, which is what people would, has pretty much displaced the regular fast SpinEcho. And so, but to understand the really fast one, we have to sort of go through the evolutionary history of SpinEcho. So back in the day, like about 1990, when I was first doing some scanning, we would actually do this original slow SpinEcho. So I'll go over that one first, because that looks just like our original diagram of SpinEcho. And so we'll just try to go over the pulse sequence diagram and then where we are in K-space. So here's on this side we'll have the K-space. There's the center of it, and then we'll draw the pulse sequence off to the right. So if you start off with with our standard 5 lines, so we've got our RF stim, so that's the actual RF transmit. And so the first thing we would do would be, since it's a SpinEcho, would be a 90-degree RF pulse to get the largest amount of transverse. And typically we would be doing this on a slice. So this would be, so I'll talk about 2D. So the really fast SpinEcho is actually 3D. But we'll talk about the 2D one first. And so for that part, we need to have the gradient on when we select a slice, so that this frequency selective RF pulse will just hit the slice that's at the right, that little slab that's at the right part of the gradient. And then we have to fix the result of that slice select pulse. So then we have I'll put our 180 here, because the SpinEcho is just a 90 and a 180 and then an echo. And so basically whatever that time is, we get our echo that amount of time later. So, but now we're actually trying to record all the data for one slice. And so what is all the data for one slice? It's going to be all the different combinations of spatial frequency in the X and the Y direction. So at this point, I'll put an A over there. So what do we, where are we after that point? And we're back at the center of K-space. Because this gradient, if this was the Z gradient, that gradient would have moved us. It would not actually be visible in this diagram because this is Kx and Ky. So what would that have done? In 3D, it would have moved us essentially to a point in Z K-space. So you could imagine here's the K-space for the X and the Y direction, but there's also a Z direction. And so when we turn that Z gradient on, it's not even visible on this diagram. It would stay at Kx ky0, but it would be sort of sticking out in 3D. But then we fix it, and so then it goes back to the center. So that's where we are at the start of the pulse sequence. And then what we do is we move to the right of k-space. And so we'll see why we want to do that in a second. So basically, here's the y gradient and the z gradient. And so after that's done, we go and move to the right of k-space. So you might wonder why the right, because that means we go over to here. So after that pulse, we're now at point B in k-space, right here. So now we're at B. So then what do we do? So let me draw it like I drew it here. So after the 180, so here's the 180. So when we do the 180, we also have to do a slice select for the 180 because we're going to be doing different slices. So here's the 180. So we do a slice select for the 180. But there's a problem with the slice select for the 180, and the problem comes from the fact that what if your 180 wasn't. Well, there's two problems. So one problem is, what if you actually had some transverse magnetization to start with? So here's a little bit of transverse. So you can see that's a little bit of transverse right here, MT. If you do a 180, you'll end up with a little bit of transverse magnetization down there. So that's one problem, and we maybe want to save that transverse magnetization. But there's another problem, is what if our 180 wasn't perfect? So if our 180 was, say, like, 170 instead, that's going to leave some transverse magnetization. So that turns out to be a problem, because we're going to, after doing this 180, record a signal, and if the signal has, which supposedly has transverse magnetization that only came from the echo, but if we've actually got some transverse magnetization that came from our RF pulse, that's going to mess things up. And so typically what happens is you have a little horn on the slice select pulse, and this thing is called a crusher. So the idea is we want to get rid of any transverse magnetization. That might have been generated by the RF pulse. But we might want to, if there was some transverse magnetization that was generated by the original 90, for instance, we might want to keep that. And so we would put a little horn on this side also, and the reason it's up is because there's a 180 in between. So what this up one is doing is it's sort of undoing the effect of the second one, pre-undoing the effect of the second one on whatever transverse magnetization might have been left at this point that we wanted to keep. So we didn't want to keep the transverse magnetization that was due to the incorrect 180, but we wanted to sort of preserve everything like it was before we started. And so this is that's a wordy, complex way of doing that. So, and then the reason it's up rather than down is because there's a 180 in between, and so basically up here equals down afterwards. So that's a way to sort of take care of an imperfect 180, and then also take care of pre-existing, restore pre-existing. So, and we have to do, that's a slice select. So normally you wouldn't have to do the corrector part for the slice select, because this shouldn't have caused any change in transverse magnetism. It shouldn't have changed your position in K-space. A 180 wouldn't. Sorry, it will change your position in case. That's not correct. It will change your position in K-space. And so what does that 180 do? So now we're at C. And so what that 180 does is it takes us to the conjugate point in K-space. So the conjugate point in K-space is if we happen to be up here, the conjugate point in K-space would be over here. If we were here, the conjugate point in K-space would be here. So that's what the 180 does. It definitely moves you in K-space. So that's where we end up after doing that 180. So we still haven't collected any data. And so if we actually look at, there's a signal that was generated by the 90, but we're not paying attention to that. So if we look at the last thing is our actual signal. So there's a big signal generated here. And there might be some of it left, transverse signal. And then we do the 180. And then, at this point, we're going to get an echo. And so that's the spin echo that we want to record. So this is where the echo comes up. But there might have been something in. There might have been some transverse in there before we. At the moment we did the 180. Okay, so now what? So now we have to. So now we're over here. Now we have to collect a line of K-space, and so for that we need our phase encoding step, which is, and the definition of phase encoding is simply you just turn on the gradient before you do the readout. And so the phase encoding step, we'll put that over here in the y direction. And so what that means is you have to repeat this whole sequence a bunch of times, setting the phase encode gradient to all those different points. And so let's assume that we set the phase encode gradient to, say, halfway up. So now the question is, where do we get to in the case of D? So now that means we're going to go in a positive direction in K-space, and so this is where we are now in K-space. And then finally we actually do a readout. Now this would be like about here. And so then after we've done the readout, here we are at point E. So that would go across K-space to point E. And then during this time we would actually record data. So these other movements in K-space, the gradients were changing the stripe pattern, but we weren't recording any data. So now we actually record a line of data. So that's the basic SpinEcho sequence. So what's slow about it? So the problem is, say you wanted to get a T2 weighted scan, so T2 weighted scans are very common because T2 weighted scans can be used to detect whether there's some a tumor will often have sort of a signature of a very bright contrast in a T2 weighted scan. And that's kind of the realization of this is essentially what drove the use of, drove all the technology to make MRI in order to be able to detect brain tumors, because you could see the strong contrast between a brain tumor and the surrounding tissue. And so that means you need a good T2 weighted scan. But the problem with that, and that would be, here, this is the curve that's, in this special case of 90 and 180 is just e to the minus t over t2. So not t2 star. And so if you want to get that T2 weighted scan, then you don't want T1 weighting in there. And so the problem is, if you've done a 90, you're going to have to wait, a couple seconds, like 3 seconds or 4 seconds. So 4 seconds later, so you're going to have a TR that's about 4 seconds. So here's the next time we do a 90. That's the definition of TR. So another 90. If you want to essentially allow the tissue to recover so that there's no T1 contrast, because otherwise you would go down to 90 and then there'd be a significant difference. You have to wait until we essentially get all the way back up there, so that there's no, and that's going to take 3 or 4 seconds. So that's a really long time. So think about how much data you have to collect. You have to collect every line of K-space, and if it's a 256 by 256 image, that's going to be 256 lines. And if you take 4 seconds to collect each line, that's a lot of lines, but that's only one slice, and now you've got to collect multiple slices. So one thing you can do is you can interleave. So basically you could say collect this slice, and then a little later in time, so here's our 3D volume with all our slices in it. And so what we could do is we could collect this slice, and then a little bit later in time, collect the next slice, or skip a slice, and so collect. If you look at the slices this way, you'll collect T1, T2, T3, T4, and then go back and T5, T6, etc. And so while you're waiting, and do those all at different times, so while you're waiting for slice 1 to recover, you can go through and collect all the rest of the slices, and then by the time you get back there 4 seconds later, you'll be able to record again with good T2 contrast and suppressing your T1 contrast. So this is the classic SpinEcho. Now, what's the problem with it? Well, it would take, even with relatively thick slices, like 6 millimeter slices, it would take something like 40 minutes to collect one of these scans. And that's what they used to do back in the day. But the problem is, you're essentially collecting just one K-space line at a time. You've got to fill all of K-space, and you've got to fill all the slices, and all that has to be done sort of, separately. And so you could, get maybe a 6 millimeter slice, which is pretty thick. It might have a 1 millimeter in-plane resolution, but the slice, it's kind of like a slab, so the voxels in this slab are like little things that go through like that. So there might be like 1 by 1 by 6 millimeters thick, and so they're going to blur in this axis quite a bit. Even that would take 40 minutes to get all the way through the brain. And then the other problem is the movement artifact, because you're collecting these lines of K-space over time, and so you don't really reconstruct the whole image until you get to the end. So so the movement artifact can occur anywhere in that 40 minutes, and that's obviously obviously going to end up with, like, very bad looking images if there's any movement. And there's no easy way to correct that. So like when I started out, we did scans just like this that were really slow. So that is not a good way to get good images. And so then people came up with an idea to essentially use a train of echoes. And so the idea here is that you're only recording one echo in this setup. Why don't we record a whole train of them? And you could sort of think of this as one of the early versions of something like echoplanar imaging, where you record a whole bunch of lines of K-space at once. And so for this method, we, however, have to sort of take into consideration where we ended up in K-space at each point in time. And so what this looks like is we do a train of echoes. And so the train of echoes was you do a 90, a 180, and then twice the distance between the 90 and a 180, you do another 180, and keep doing that, and you'll get a series of echoes. So if we draw this sequence out, so this one's called turbo SpinEcho. It's called sometimes it's called fast SpinEcho, or sometimes it's called turbo SpinEcho, or sometimes it's called rare. I can't remember what that means, but probably turbo SpinEcho is the one that's most commonly used. And so the idea is we want to collect multiple lines of K-space just from one 90. And so here's our the RF stimulation. There's a 90 here. So the 90s are the most radioactive ones in a way, because when you do that, it's going to take a very long time to recover. So then, just like before, we would do a slice select, and then here's the slice select fixer. So that's it. So we're selecting a slice in the Z direction, and we could all these things would be written out differently if we're doing a different axis, but usually there's kind of the default. You sort of by default consider Z to be the slice direction, and then just say everything would be different, but we'll just always put the slice selection on Z and the phase encode on Y and the readout on X. So that's our slice select, and then we have to do another. We do our go to the right side of K-space. So if you remember, I didn't say it last time, but when we were doing a gradient echo, typically what we would do for the readout, gradient echo, we would typically do first go to the left side of K-space and then go to the right side of K-space, go all the way to the right side of K-space. So like start in the middle, go here and then come back across. We're doing that here, but the reason that this one is positive is because there's a 180 coming up and the 180 flips things. So now we got the 180 coming up. And so that will flip things. So just like last time, so here we're at the center. We go back to the center of K-space, and then here we go to the right side of K-space. And then right after the 180, I'll put the C up there. So here's A. So we came out in the Z direction and went back here. And then we go over to B, go over to the right side, And then we go to the conjugate point, turn around and go to the conjugate point over here. So that was the RF pulse. So that was C. And then we do, and then during that we have to do our slice. We have to slice select again because we want to get the same slice for our 180. And then we do the a particular phase encode step. So we do so pick out one of those phase encode steps here, and then so that say if we pick out this one, then that's D. So that would make us go up here like we did before. So D. And then finally we do a readout. It has to start after that. So here's our readout. And that would just turn around and go right back across. Oops. It would turn around. It would go across K-space here. That's where we collect all the data for that line. That's E. So that's E over here. Okay, so now, and that would give us our echo, which would be here. This is our SpinEcho, and here's the initial FID we ignore. Okay, so now the problem is if we want to do an echo train, what will we do? We would take this time. We could take this time here and double it. So that time is our time tau, so we would do that amount of time, and that's when the echo occurs, but then do that amount of time again, and then do another 180. And that's how we would get an echo train. But there's one problem, is that we're now sort of like over here in K-space. And so what we need to do is to do a fixer. So we need to do a fixer phase encode. So so we stick this in here. There's a little fixer phase encode. And it's going to be exactly the opposite. So whatever we did this time, we'll do the opposite of it. So this guy, we do the opposite of it each time. So if we went up over here, we have to go down before the 180. And so what that will do is that will put us back at position DEF. So here we're back at position F. So position F is do the reverse of this phase encode, so we get back down to here. So that's point F. And now we're ready. We only need one of these. So only one of these. Only one of these. So we only need to do that the first time, because here we ended up at the same place where that thing put us at. So basically, we'll go back to where we were at point B after this, and then pretty much we're ready for another phase encode. So here's another phase encode. So sometimes when people do this, we put an arrow in here, meaning like we do all those in that order, and then these guys are all those in the reverse order. So these are sort of like canceling out what this one did. And so now we've got another one of these guys. Pick out a different one, and then after that one is, so say we tried a negative one there. So let's say we try a negative one there. So in that case, what would happen is, after we still have to put in C, D, E, F, G. Here's G and H. So G, so E, F. So G is going to G is going to flip us back to this side. So here's G. And then now we did a negative 1. So here's G. And now we did a negative 1. And that negative 1, say, maybe put us down here. And so that's H. And then we go across, do the readout, go across to HI. And then we do the readout, then we do the phasing code fixer. So here's the fixer for this one, which is going to be positive instead of negative, and that will IJ. So that's J. So now we're ready to repeat. Okay, so we did GH, and then we did the readout. And at the end of the readout, we were at I, and then we have to do another version of the fix the phasing code, but in this case we do the opposite again, so we use that one. Okay, so now we just did 2 cycles of it, and then we would have gotten an echo over here like this. And so then you just keep doing that for maybe like 16 echoes or something. For example, 16 echoes. You could even do like 30 echoes. So what's stopping you from doing more? You might think, why don't we do like 60 echoes or something like that? And so what stops you from doing more is the 180s. And the reason that is because the 180s deposit a lot of power. And so we could write down what the equation for the approximate equation for the deposition of power is, but it's if you compare a 90 to go to 180 degree flip is actually about 6 times the power. So it's 6 times as expensive to do a 180 in terms of heating up the subject. And there's a limit to how much you can heat up the subject. You don't actually want to warm them up more than about a degree. And the scanner takes very careful record of how much RF power you've deposited in. It actually directly measures it by, so if you put a RF pulse, some of it will get absorbed, but the part that doesn't get absorbed will be reflected back. And so you can measure exactly how much RF power went into the sample, which is you. And so the scanner carefully measures that, and it measures it and predicts how fast it takes. It makes quite a good prediction about how fast that heat is going to be dissipated, because it's something like the brain, the heat, the small amount of heat is dissipated very quickly because the brain is tons of blood flowing up through the brain. It's like a finger or something, so there's a lot of blood flowing through it, and so if you slightly heat it, it'll immediately get rid of that heat by dissipating it to the rest of the body. So you have to model that as well, but what you can do then is you can very carefully monitor how much RF power you deposit into the subject. And so one of the problems is since a 180 is so much more power than a 90, you can't do that many of them, and that's actually one of the things that constrains how many echoes you can do, because you might be able to do this more like echoplanar, where you do really rapid set of echo trains, and then you could collect the data in much less time. So that's one of the problems that stops you at, say, something like 16 echoes. But there's another interesting thing, which is what kind of contrast do you get out of this? And so I described this typically as a way to get good T2 contrast. So now we're getting 16 lines of K-space for every 90-degree RF pulse. And then we have to wait, 3 or 4 seconds for the magnetization, the longitudinal magnetization to recover before we can do that slice again. But we got 16 16 lines of k-space. But when you think about this, you can see this is something that happens with all sort of more advanced pulse sequences. We're ending up in a strange world where we collected different parts of k-space with different amounts of T2 decay. So if you look at this curve here, you can see that this echo, so e to the minus t over t2, this echo is at a longer time than the first echo. So that means that the amount of T2 decay that occurred is different in the different parts of k-space. That's kind of strange, because normally you're thinking, what we want to do is select a particular echo time, and then look at differences. So I mean, what is contrast? Well, contrast is going to be, differences in this T2 decay curve. It's kind of hard to see at that scale, but what are we looking at? We're looking at, something that we're trying to figure out the difference between this tissue and this tissue. Now, and we're wanting to say, I want, that difference between these two tissue types. But the problem is you're recording these echoes at all these different times. And so that means different spatial frequencies are going to have different weighting, different T2 contrast weighting, which is kind of strange. It's just say a high, so if we record this echo very early, it's not going to have very much T2 weighting at all. And if we record an echo, later in time, it's going to have more T2 weighting. So at first it seems like that's just such a strange thing. How could you actually get any kind of consistent T2 weighting? But the way this works is that you mainly pay attention to, mainly attend to k-space center. So it turns out that one is the one that most strongly affects the overall contrast of the image. And so one thing that's done with this kind of scan very commonly is to arrange to record the k-space center at different times. So if you record center early, then you'll get a proton density scan, because there hasn't been any. It's like if you record the center early, there won't be any contrast between these two tissue types, and so you'll basically get something that, and there's no T1 contrast because we're doing a long TR. I should draw in here. So then eventually we get back to another 90, and that's the TR. But that could be something like 4 seconds. So here's the next one. TR. For example, 4 seconds. So what is, how does this work? You do like a 90 and then a bunch of 180s quite close in time, and then you wait a long time while you're doing the other slices, and then you do after 4 seconds you do another 90. So all these echo trains are occurring over a much shorter time than TR. So, but just back to this, if we record the center of k-space early, we get a proton density scan. If we record it late, so that's just when we decide to go through the center of k-space here. Record center late, then you get a T2 weighted scan. And so what you can do is you can just do both. So you could just record all the echoes and then go through the center of k-space early, and then also go through the center of k-space late. And then mix together all these different spatial frequencies that have different amounts of T2 decay, and what you get is something that really looks proton density weighted, or something that really looks T2 weighted. It's quite amazing. So sometimes if you look in textbooks, you might see something where they show you the the amplitude of the echoes. I remember when I first looked at this, I said, how could that be? And they would show the echoes, going up and then going down. And that didn't make sense. But what that comes from, the different echoes, these different echoes here, how you could do something like this is just record the center of k-space late. If you record it late, even though there's been T2 decay, the center of k-space is always going to be bigger than any other part of k-space. And so that could make the center of k-space echo bigger than this initial echo. Alternatively, if you record the center of k-space at the beginning, then so each one of these is an echo with a bunch of wiggles in it. You would end up with something that looks like that, where the first echo is much bigger than the rest of them. So this is basically a way to get a SpinEcho image, but get a lot more data, like 16 times as much data. So it's turbo. So the idea is that this will actually just go 16 times faster than a slow SpinEcho. Just about 16 times faster. So that's a really big difference. And so now you could get it down to like a 5-minute scan, a 5 or 6 minute scan at a reasonable resolution. It's still not, typically the slices are still going to be relatively thick, but they're going to be much quicker to collect it and much more sort of usable for the subject. So this is still sometimes done, and you might wonder, like, why do this when you have a scan that I'm going to talk about next time that gives you 3-dimensional data at a very even higher resolution than this, even less time than this. And it's interesting when you look at this from the point of view of diagnosis. One of the things that a thicker slice does is it blurs out small defects. And one of the problems with MRI is that it shows you so much stuff that most of it is kind of irrelevant. You'll see like a little blip here. Maybe there's a tiny stroke that occurred over here, or maybe there's a tiny little growth over here that's kind of irrelevant, or maybe a little cyst. So you'll see a bunch of little tiny things. One advantage of thicker slices is it blurs all those out, and so you just see like, oh, that is a bad thing. That's a sizable tumor that I can see that even though I blurred it through the thickness of a 4 or 6 millimeter slice, it's kind of, you can think of thick slices as a conceptual filter that will sort of filter out these small irrelevant parts of the scan and just show you stuff that kind of sticks out from normal. So even to this day, people still look at these relatively thick slices for that reason, because it just kind of like blurs out some of the irrelevant noise in the image and shows you like something that's worth following up on. Okay, so that was fast SpinEcho, 2D fast SpinEcho, turbo SpinEcho. And so what I want to do is just for about 2 minutes, just switch gears to talk about something that I forgot to talk about at the beginning of the class, which was that's relevant to the wraparound. So I'll just mention quickly, wraparound. So if you look on the scanner, so this is sort of backing up to wraparound replicas. So backing up to what we talked about last time. So one of the things that happens with something that anybody who uses, like a clinician who uses a scanner would know, is that wraparound occurs in the phase encode direction. And it doesn't typically occur. It doesn't. We'll show that it actually doesn't occur in frequency encode. And so this, again, you might think, oh, well, frequency encoding is fundamentally different. Didn't Marty say that, frequency encoding and phase encoding were exactly the same? And they are. And wraparound occurs in the frequency encode direction. It definitely occurs just the same way because there's replicas in the frequency encode direction, there's replicas in the phase encode direction. The phase encode direction and frequency encode direction are just two equivalent dimensions of k-space that are only really distinguished by what direction the gradient is on. So how could it not occur in the frequency encode direction? And so the reason it doesn't occur, there's basically two ways to fix this. So the first is you could just, because we're doing a readout, we could just sample twice as fast. So if we just sample, if we sample like half as fast, we get a certain field of view. If we sample twice as fast, that just doubles our field of view. So there's two things we could do. So one, we could just sample twice as fast, and that will push the replicas out. And it's not hard. We're not losing anything by sampling twice as fast, because we've got to we've got to leave the gradient on this long in order to get up to a certain spatial frequency. And so all we do is just, so it doesn't take any time. We just sample twice as fast. Everything is good, pushes the replicas out. Now you can't do that during, it doesn't occur. It does occur. It does occur in the frequency encode direction, but you can't do this sampling twice as fast business with the phase encode because you're basically only doing, that's done before the recording, and so whatever you set the phase encode to, it's your one sample of the phase encode direction, and so there's no way to sort of sample that twice as fast because, you've just set it to that amount of phase encode, and now we're going to do a sample at that phase encode. So you can't, you can't do this trick. Can't do trick in phase encode. But there's another tricky trick, which you also can't do in phase encode, which is just filter out the high frequencies. And so this is another. Marty said, don't think of frequency encoding as all these simultaneous frequencies being on and Fourier transform somehow sort of fishing out those frequencies. That's correct. You should not think of frequency encoding that way. You should think of it as just wrapping up the spins just the same way that the phase encode does. But you can take an analog, not an analogy, you can take an analog filter, so you can just analog filter out signal off the edge. And so this is taking advantage of the fact that, in fact, there are multiple frequencies being emitted. That's irrelevant for thinking of it in terms of k-space. It's not a way to think of spatial frequencies. There's multiple temporal frequencies. Those are not spatial frequencies. So here's different spatial frequencies as we go through the readout. During that entire time, there's multiple temporal frequencies because the guys at the high end of the gradient are as soon as you turn the gradient on, the guys at the high end of the gradient are precessing faster. And so you can analog filter those guys out. And so what do those correspond to? Those correspond to parts of the brain that are off the edge, also known as wraparound. So you can analog filter out signals off edge. And so then what that will do is that will essentially remove the replicas that were off the edge of the, essentially off the edge of the field of view that we want to look at. So it's a weird, if you can understand this, it's a weird twisting of ideas, because here you're sort of like going back to the spectroscopy picture to filter out these things that are off the edge. Now, this is another one that you can't do. With phase encode. And it's a different reason. The reason you can't do it with the phase encode is that when you turn the phase encode on, the frequencies, changed at the high end of the gradient, and then cause some spin wrap, and then you turn the gradient off, and so now the frequencies are all the same in the y direction. And so that you can't do this trick, can't do it with phase because phase gradient is off. So you can't do that one with phase either. And so those you can do both of those things, and so that will basically eliminate. That basically eliminates wraparound in the frequency direction, but that doesn't mean it's not there. It actually is still there. You still got the same problem because conceptually it's the same replica problem in the frequency encode direction, but there's an easy way to fix it. But it's relevant to the scanner, so when you're on the scanner, the frequency encode direction is not going to wrap around. And so if you've got like a long body or something like that, then you would want to set the frequency encode direction along the body if you just want to select a chunk of the body and not have wraparound outside the body. Okay, so that was sort of just finishing up something that I forgot to mention at the beginning of class. Okay, David, I think we'll end the recording there.